Welcome to one of the most persistent mysteries in statistics, the n-1 dilemma. If you've ever calculated a sample variance or standard deviation, you've seen it. Instead of dividing by the total number of data points, n, we divide by n-1. This adjustment is known as Bessel's correction. But why? Why do we lose a degree of freedom? Today, we will solve the n-1 mystery through intuition, algebra, and geometry. Section 1. The intuitive concept of freedom. To understand degrees of freedom, think of it as the freedom to vary. Imagine you are inviting 3 friends to a dinner party where there are 3 menu options: pizza, sushi, and tacos. The first friend arrives and has 3 choices, total freedom. The second friend arrives and has 2 choices left. But the third friend? They have 0 freedom. Their choice is predetermined by what's left. In statistics, when we fix a parameter like the sample mean, we are imposing a constraint that uses up one of our choices. Section 2. The mathematical constraint. Let's look at the math. Suppose we have a sample of 3 numbers, x1, x2, and x3. If I tell you the mean, x bar, of these numbers is 10, how many of these numbers can you choose freely? You can pick x1 to be 8 and x2 to be 15. But once those are chosen, x3 must be 7 to keep the mean at 10. Mathematically, the sum of deviations from the mean must always equal 0. Because of this equation, only n-1 values are truly free to vary. The last one is locked by the others. Section 3. The problem of bias. Why does this matter for variance? Variance measures how far data points are from the mean. If we knew the true population mean, mu, we would divide by n. But usually we don't know mu. We use the sample mean, x bar, instead. The sample mean is calculated from the data itself, which makes it closer to the sample points than the true population mean would be. Because x bar sits right in the center of our sample, the squared distances to x bar will always be smaller than the squared distances to the true mu. Section 4. Bessel's correction and underestimation. If we divide by n when using the sample mean, we will consistently underestimate the true variability of the population. This is called bias. Statistical simulations show that dividing by n creates a downward bias of n-1 over n. To correct this and get an unbiased estimator, we multiply by the reciprocal, n over n-1. When you simplify the formula, the n cancels out, leaving us with the famous n-1 in the denominator. This is Bessel's correction, named after Friedrich Bessel. Section 5. The geometric perspective. For the visual thinkers, imagine your data as a vector in n-dimensional space. In a sample of size n, the data lives in an n-dimensional volume. However, when we calculate the sample mean, we are projecting that data onto a specific hyperplane. The residuals, the differences between the data and the mean, actually live in a subspace with n-1 dimensions. You literally cannot move in n directions anymore. You are restricted to an n-1 dimensional flat surface. Conclusion: the logic of accuracy. Subtracting 1 isn't just a mathematical quirk, it's a necessary adjustment to ensure our sample estimates are honest reflections of the population. By dividing by n-1, we compensate for the fact that we use our data twice, once to find the center and once to find the spread. Now the mystery of n-1 is solved. References: Gujarati D9, Basic Economics, Casella G. and Berger R.L., Statistical Inference, Friend J.E., Mathematical Statistics with Applications.